Hello and welcome to Calculus. This is video lesson 5 of 6. There'll be this and then one more in section 3.1, 3.2, the beginning of our derivatives unit. So we talked about the idea of one-sided limits and what it means to differentiability and a couple other notation things in the last video. In this video, we're going to start to relate the graph of a function to the graph of its derivative. Now, back when you did lines, equations of lines, the graphs of derivatives were very boring because the whole point of a line is its slope is constant. So if you had a graph, let's say you had a graph of I don't know why this is erasing on me. If you had a graph of a line, because I'm not on the document, that went something like this. And you had the graph of the line. Let's say that's the graph of the line y equals 2x plus 1. That's not, that means that would be a 1. The y-intercept, just a little review. And the slope is the number in front of the x. If I said graph the slope, well, y prime is always going to be 2. It is a constant. Derivative is a slope. Yeah, that's the big concept going on here in calculus. So if I said graph its slope, well, that would be pretty boring. You would draw a graph that went something like this. Oh, the slope is always 2, and this would be a horizontal line at 2 if this was y prime. So when you have a line, your graph was just a number. So we never bothered sketching the graph of a slope of a line because it was always just a horizontal line at the number that was equal to the slope. Now what you'll notice is this line has a positive slope. It goes up. The number 2 is positive. It goes up. The graph of this slope, even though it's a boring horizontal line, is above the x-axis. Anything with a positive value, so if I'm graphing slopes and they're positive, they're going to be above the x-axis. And if the value of the slopes are negative, they're going to be below the x-axis. So if my graph was negative 2x plus 1 and went the other way, I'd still have a horizontal line, but it would be down here. So that's something to keep in mind as we look at the relationship between graphing functions and derivatives, or taking a function and graphing its derivative. Mostly for this unit, you'll be held to matching the graph of a function to the graph of its derivative, and I'll show you some key things to look for. When we get into the unit of applications on derivatives, which is the third unit, chapter 4 of the text, then we'll talk a little bit more precisely about graphing derivatives. But for now, I'm going to want you to be able to match the graph of a function to the graph of its derivative, and that will step you through the big things you look for here. So, okay, I think I'm going to erase my scribbling here. I'm not going to erase it if I don't pick up an eraser, am I? Okay, so I'm making mistakes here just like I would if we were in face-to-face class, just so you don't miss those days. Okay, let me pick up my pen again. So, these are the key points here. When your function has a horizontal tangent line. So what do you mean tangent line? Remember, tangent line, if I want to draw a tangent line to my graph here at this top, the tangent line is going to be horizontal. The slope is 0 at the top here, and that'll be a key point we carry through with us for the rest of the course. Where the function turns around, here it had a positive slope, and the other side is a negative. At some point, that slope must have been 0. There's your intermediate value theorem in action. So where I have a horizontal tangent, that means the slope was 0. So every place I have a kind of a turnaround where this is continuous, I am going to have a 0 on the graph of my derivative. So that is one of the things you look for. You see here at x equals 4, I have a minimum. That means I turned around, and so I have a 0 there, and I have a 0 there. When we see this again in Unit 4, we're going to also learn that this was a minimum because the derivative went from negative to positive. But for now, you're looking at the function and picking up the tops and the bottoms and saying that's where my derivative will be 0. So wherever you have a positive slope, so go through and label these. From in this section, so these points I've picked out here are going to be our breaks in the interval between positive and negative slopes. Slope is positive up until I get to that point just before x equals 0. I guess it's It's about x equals negative a half. And then my slope is negative down to here, and then again it's positive over here. So what I see is this is a graph of the derivative. It's already been given it to us, so we're just analyzing it. The slope is positive, and look, the steeper the graph is, so this is positive, so the value of the slope will be graphed above the x-axis. We know that. But the question is, how far above? Do I put it here? Do I put it here? Do I put it here? The steeper the graph is, the further above the axis, the higher the value of the slope. The absolute value will be a bigger number. So notice this is steep, and it gets out. And as you get towards a turn, you always get a little less steep. Your slopes of your tangent lines get smaller and smaller until you get to 0. So it kind of bends over like that. You start out steeper and end up flatter. So you start here and you move your way down. I'm sorry if you're seeing those email notifications there. And you go down. So you're definitely on the positive side of the x-axis, and it's steeper here. So you start out with x being the value of the slope being steeper, further out x is to the left, and it comes down until you get to 0 at this point here we already talked about. Then your slope is negative. Well, it starts out kind of flat, gets steep, and goes flat. So you got to make your way negative, and we're not going to be too worried about exactly what these numbers are when we match our sketches. We just want to see that my slope is negative. It gets steeper and then gets flatter as I come to the point where it turns, which is what differentiable functions will do. And then I've already put this 0 here. So I know I had to start out here. This is a little bit like sketching polynomials in pre-calculus. And then, well, from x equals 4 on, my slope is positive. So you can see from x equals 4 here, I am above the axis. So you get the general shape. And some of you are saying, well, this looks like this is a 3rd degree polynomial. The highest exponent will be a 3. And this one looks like some form of an x squared, a quadratic. That's right. You lose a degree every time you go from a function to a derivative if you have a polynomial. And we'll see that as we move forward. So if I had 2 turnarounds in my function, I have 2 zeros in my derivative. Okay, if I have 2 zeros, the most times my function can turn around is once. This function had 3 zeros, so it can turn around twice, but I had 2 turnarounds here. That gives me 2 zeros, which means I can every polynomial, at least for polynomials, every polynomial can only turn around 1 less than the number of zeros it has. It can't be as many as the number of zeros it has. So the main ideas are, when your function has a positive slope, the graph of the derivative is above the x-axis. When the function has a negative slope, the graph of the derivative is below the x-axis. Where you have a corner cusp or vertical tangent or vertical asymptote, it is undefined. We don't have that in this graph. But if you have a sharp point, or you have an asymptote, which would be a discontinuity. Any place you have a discontinuity, you don't have a derivative to plot at that point. That x value will not be in the domain of your derivative function. So let's move down to this one and take a look at trying one. So you want to graph a continuous function with the following. So this is continuous. You're not going to have any trouble with jumping around or anything. Following characteristics. Now, it's simple things that confuse us in calculus sometimes. F of 2 equals negative 3. That means I have the point x is 2, y is negative 3 is on my graph. So I go over to 2 and I go down to 3. I'm having a little trouble seeing that there. There we go. And I put that point. F of 5, oh, yeah, I did 2, negative 3. F of 5 is 3, so I get the point 5, 3 on the graph. 5, 1, 2, that looks like 3 there, right there. And f prime of 2 is 0. This means I have a turnaround there. Now, I don't know whether I turn around going like that, or so f prime of 2. So whatever's going on here, I'm turning around. Am I turning around like this, or am I turning around like that? I don't know yet until I look at this. The derivative before I get to 0. The derivative before I get to 2, sorry. Derivative before I get to 2 is negative. I see that less than 0 and I say in my head negative. Even I still do that after 24 years of teaching math and many more years of doing math. This, I know what it means, but it has more meaning if I translate it in my head to is negative. So the derivative is negative there. It's 0 at 2, and it's positive after I get to 2. So negative derivative means my function is tending downward. Positive derivative means my function has a slope that's positive, it's upward. So until I get to, so I have f of 5 is 3, so, and I know I turn around at 2. Before that I was negative, so I must come down to the 2 and turn and go up there and cross through there. And that's all I know. Your graph might be a little different than mine. But what you have to have is this point, 2, -3 on there. And to reach that point, you came down using a negative slope, and you turned around at that point because you were told f prime of 2 is 0, and then you had a positive slope. So that's one way to graph a function with these characteristics based upon what we know about the sign of a derivative and what happens when the derivative is 0, being a place that it turns around. Those are the big things to remember here. Okay, we're going to look at differentiability in the next and final video for this section. Thank you for joining.